Here we go. The last piece. Lego is so satisfying. The idea that you can build almost anything out of these small plastic pieces. That if I broke this up, it would just be tiny little individual pieces of plastic. This idea is very similar to the atomic hypothesis, the idea that everything is made out of atoms. But as an idea, it's not one that we've always had. The idea goes back all the way into ancient Greece, and it's been a long road to discover what atoms are like.
Democritus of Thrace, an ancient Greek philosopher from 460 BC. Democritus had this idea, and it was about matter, that either, and he used the example of a cake being sliced, that matter could be divided infinitely, so that the cake, sliced again and again and again, you could continue to do this forever. Or, alternatively, you would reach a basic building block, an ingredient of the cake that itself could no longer be divided. Like the Lego, he had stumbled across the idea that maybe matter itself was made out of tiny little particles. And these were called atoms.
Democritus had the idea that all atoms were identical little billiard balls, like this. And that was enough to explain why things were solid, because you couldn't push them any further together. But it wasn't enough to explain how different substances are different from each other. The ancient Greek philosophers had ideas of mixing the four elements, earth, air, fire and water, to create everything we saw, but it was too primitive. It required the invention of chemistry as a discipline before we understood that actually these atoms can be different from each other, and that is the elements, the isotopes or the ions.
It wasn't until 1897 that Joseph John Thomson, also known as J.J. Thomson, discovered the electron, and through investigations of static electricity came to the startling conclusion that atoms contained positive charge and negative charge. But how was it arranged?
Thomson then had the dilemma of figuring out how could positive and negative charge both exist within an atom, which, using the ancient Greek idea, was just a hard billiard ball. Well, he came up with this. It's called the Plum pudding model. He thought that the negative charges, the electrons that he had discovered, were perhaps interdispersed within an atom, like the plums in a Christmas pudding. And that's why this is called a plum pudding model. The red on this model represents a region of positive charge, the kind of cake, and the green represents the negative electrons. And at any point, one of these electrons could be pulled out, and that would explain how an ion could form. And they also explain how J.J. Thomson could isolate an electron and bring it out of a neutral atom.
Then, in 1911, Ernest Rutherford, a New Zealand physicist working in Manchester, had an idea about how to probe matter at its smallest levels. He had the idea that if you fired alpha particles, which we'll talk about later, small charged positive particles at some gold leaf, then what we normally see is they get absorbed and they can't go through. But what would happen if you press the gold leaf so that it was thinner and thinner and thinner until it was just one atom thick? At that stage, if the plum pudding model was correct, you would still expect that the alpha particles would be absorbed. What was seen by his two students, Ernest Marsden and Hans Geiger, was very different indeed.
So this is the basis behind Ernest Rutherford's experiment. This here is emitting some invisible positive particles that we call alpha particles. And you can't see them, and they don't interact with anything visibly. But here we've got a device which enables you to see
those particles colliding with this screen. Now this screen is actually called a spark counter. The one in Rutherford's experiment was actually a scintillating screen, but it was basically the same thing. Now what Rutherford wanted to do was to examine what happened when ever thinner slices of this gold leaf were placed between the source and the detector. What you can see with this, and I'm going to just turn it off while I put it on, is that if I slide the gold leaf over the detector like this, and then turn it on, it has become slightly charged up. But you can see that here, none of the alpha particles are getting through. And that's because this gold leaf is too thick. But what happens when we get it so thin that it is almost one atom thick? Does the alpha particles get absorbed by those plum pudding atoms, or does something else happen? Here I have a model of Rutherford's scattering experiment. Instead of alpha particles, I'm going to use ping pong balls. Now what was noticed in the experiment was that most of these alpha particles flew straight through. But some did something quite remarkable. Every now and again, one of the alpha particles was deflected. So what was happening? Well, imagine that this is our atom, and this is the hypothesized nucleus that Rutherford was there. What was really clear, and the marbles here are the alpha particles, is that some of the alpha particles just went straight through the empty space. Some of the alpha particles were deflected slightly. Some of the alpha particles, to Rutherford's great surprise, came back again, meaning that the nucleus had to be positively charged, and that changed our understanding of what atoms were like. Understanding the atom like J.J. Thomson's plum pudding model was at odds with Rutherford's scattering experiment. You couldn't have the alpha particles travelling straight through this solid ball. And so Rutherford changed the idea. His scattering experiments seemed to suggest that there was a positive conglomeration of matter in the centre of the atom, what he called the nucleus. But where were J.J. Thomson's electrons in that case? Well, the hypothesis went that those electrons would be dispersed around the outside. This meant that an alpha particle could quite happily travel through the empty space, but on hitting the nucleus, the positive charge of the nucleus would repel the positive charge of the alpha particle and send it back again. This was the discovery of the nucleus. In 1913, the Danish physicist Niels Bohr came up with calculations that suggested that the electrons actually existed at certain energy levels around the nucleus. The idea, very similar to the orbits of the planets around the Sun, was that electrons occupied certain distances, and that moving between one place and another place resulted in either the absorption or emission of light. Niels Bohr's atom was basically an organisation of the electrons into orbital shells. This matched observation, because if an electron received energy in the form of a bit of light that was equal to the energy difference between these two shells, the electron would physically move, absorb that radiation, and we'd observe that wavelength of light missing in a spectrum. Shortly afterwards, it would drop back down again and re-emit it in a random direction.
This, the Bohr model, almost completely explained everything that we could see to do with the atom. But there was one further observation that fundamentally changed our picture of the atom.
In 1932, British physicist James Chadwick noticed that an uncharged particle was occasionally seen coming out of certain atoms. His hypothesis was that the nucleus could not be just a solid ball of positive charge, that within it there must be some neutral points as well. These neutral particles he called neutrons. Of course, if there were neutrons in the nucleus, the positive charges must be themselves small particles interdispersed with those neutrons, and so was discovered the proton. And this brings us pretty much up to date with our ideas about the structure of the atom.
So with Rutherford's nucleus and Bohr's electron structure, it only required Chadwick's neutron to change the picture to the modern day model of the atom, with protons in red here with a positive charge, the same in number to the green electrons around the outside for a neutral atom, but also these neutrons, neutral particles that act as a kind of glue sticking all those positive charges together. This is the model of the atom that we will use for the rest of the course.